Okay, this is the second part of lecture number 6. In the first part of lecture number 6, we discussed the root mean square value of the AC voltage. In this particular class, we are going to discuss the root mean square value of the AC current. Well, as you guys know that the root mean square value of the AC voltage or the root mean square value of the AC current is a constant value. Why? Because we compare the AC current with a DC current. And as a DC current is constant, so this is why the root mean square value of the AC current is a constant value. So let me explain the root mean square value of the AC current with the help of these two diagrams. In this particular diagram, we have connected an AC voltage source across the resistor. So there is an alternating current in the resistor, and due to this alternating current, the resistor will consume some power. The resistor will take an average power from the AC voltage source. So this resistor will take some power from the AC voltage source, and we connect the same resistor across the DC voltage source. So there will be a DC current in this resistor, and this resistor will take some power from the DC voltage source. And if the power taken by this resistor from the DC voltage source is equal to the power taken by the same resistor from the AC voltage source, then under this condition, the root mean square value of the AC current will be equal to this DC current. So the effective value of the AC current or the root mean square value of the AC current will be equal to this DC current. And you know that this DC current is constant with respect to time. This is why the RMS value of the AC current is constant with respect to time. So let us consider this particular circuit. We have connected a resistor across the DC voltage source, and the power taken by this resistor from the DC voltage source is equal to I square R. So this is the power which is taken by this resistor from the DC voltage source, and you know that this power is in terms of current. In the previous class, we calculated the powers in terms of voltage. In this particular class, we are going to consider these powers in terms of currents. So we know the equation for the power which is taken by this resistor from the DC voltage source. And then we consider this particular circuit. We have connected the same resistor across the AC voltage source, and if we apply KVL to this particular circuit, according to KVL, Vs will be equal to Vr. You see, the sum of the voltage rises in this loop will be equal to the sum of the voltage drops. So the voltage across the resistor will be equal to the voltage across the source. And we know that we have got an AC voltage source in this particular circuit. There is an AC voltage across the resistor, and the AC voltage varies sinusoidally with respect to time. AC voltage is a time varying voltage, so the voltage across the source is equal to Vm sine of omega t. So this is the equation for the voltage across the resistor. Why? Because Vr is equal to Vs. So we are going to find out the AC current in this particular circuit. The AC current in the resistor will be equal to voltage across the resistor by resistance of this resistor. And we put the value of the value of the source voltage in this particular equation. If we put the value of the source voltage in the equation, which is this particular equation, let me encircle this equation. So if we put the value of Vs in this particular equation, we get this particular equation for the current. The current will be equal to Vm sine omega t by R. And you see the alternating current changes sinusoidally with respect to time as well. This is a time varying current. So an AC current is a time varying current. It changes its direction with respect to time. The magnitude of this current changes with respect to time as well. So we know that the maximum value of the current will be equal to Vm divided by R. Vm by R gives you the maximum value or the peak value of this particular current. And if we put this value in the previous equation, so this is the equation for the AC current in the AC circuit. You see this current varies sinusoidally with respect to time, and I is equal to Im sine of omega t. Im is the maximum value of the AC current, and this maximum value of the AC current is also known as peak value of the AC current. So the power taken by the same resistor from the AC voltage source is equal to I square R, and I is an AC current. So we put the value of the AC current in this particular equation. So the power taken by the same resistor from the AC voltage source is equal to Im square R sine square omega t. So this is the instantaneous equation for the AC power which is taken by the same resistor from the AC voltage source. We want to calculate the average value of this AC power, and you know how do we calculate the average value. So let us discuss the average value of the AC power which is taken by this same resistor from the AC voltage. So the average value of the AC power taken by the same resistor from the AC voltage source is equal to 1 over 2 pi integration from 0 to 2 pi of PR d omega t. So we can compute the average value of the AC power with the help of this particular equation, and we put the value of this PR in the equation. In this particular equation, we know that the instantaneous value of the power is equal to I square R. So we calculate the average value of the AC power with the help of this particular equation. The average value of this power is equal to 1 over 2 pi, the integration from 0 to 2 pi of I square R d omega t. And we compare this power, this is the average value of the AC power, we compare this power with the power which is taken by the same resistor from the DC voltage source. So the same resistor takes a power of I square R from the DC voltage source. So if the power taken by this resistor from the DC voltage source is equal to the average value of the power taken by this resistor from the AC voltage source, then under this particular condition, the RMS value of the AC current will be equal to this DC current. So if the DC power is equal to the average value of the AC power, then under this particular condition, the effective value or the RMS value of the AC current will be equal to this DC current. So we compare the DC power with this AC power. So I square R is the DC power which is taken by this resistor from the DC voltage source, and on the right hand side of this equation we have the average value of the AC power which is taken by the same resistor from the AC voltage source. And as these two powers are equal, this is why the effective value of the AC current will be equal to the DC current I. This is why the effective value of the AC current is a constant value, because we compare this AC current with the DC current, and DC current is always constant with respect to time. So we simplify equation number 3.27. The simplification of equation number 3.27 gives you this particular equation: I square is equal to 1 over 2 pi, the integration from 0 to 2 pi of I square d omega t. And if we simplify this equation, then we get the root mean square value of the AC current. The root mean square value of the AC current is equal to under root 1 over 2 pi, the integration from 0 to 2 pi of I square d omega t. So we can calculate the root mean square value of the time varying current with the help of this particular equation. So if a current varies with respect to time, then we will use this particular equation to find out the RMS value of the time varying current. And we will use this particular equation if we have omega t along the horizontal axis. We will look at the waveform of this time varying current. If omega t is along the horizontal axis, then we will use this particular equation. And we will look at the waveform of the time varying current. If time is along the horizontal axis, then we will use this particular equation. If the time is along the horizontal axis, then we will use this particular equation to compute the RMS value of the time varying current. So we will do a lot of numerical examples, and these numerical examples will be based on these two equations. We will look at the waveforms of these time varying currents. We will look at the horizontal axis. If omega t is along the horizontal axis, use this particular equation for the calculation of the RMS value of the AC current, the RMS value of the time varying current. And if time is along the horizontal axis, then use this particular equation to find out the RMS value of the time varying current. So we will use these two equations, and we will find out the root mean square value of the time varying current with the help of these two equations. So we consider this equation now, and we put the value of the AC current in this particular equation. We know that the AC current is a time varying current. This current varies sinusoidally with respect to time. We know the equation of this particular current. We know that this current is equal to Im sine omega t. So let us put the value of this AC current in this particular equation. If we put the value of the AC current in this particular equation, we obtain this equation. The RMS value of this AC current will be equal to under root Im square by 2 pi multiplied by the integration from 0 to 2 pi of sine square omega t d omega t. And we know that sine square omega t is equal to 1 minus cos of 2 omega t by 2. So what we do, we replace sine square omega t in this particular equation by 1 minus cos of 2 omega by 2. So if we replace sine square omega t by 1 minus cos of 2 omega t by 2, we get this particular equation. The root mean square value of the AC current will be equal to under root Im square by 4 pi, the integration from 0 to 2 pi of 1 minus cos of 2 omega t d omega t. And you see there are two terms under the root. So let us simplify this equation. The root mean square value of the alternating current will be equal to under root Im square by 4 pi, and we have the integration of the first term. The first term is d omega t. We integrate this term from 0 to 2 pi, then minus sign, and we integrate the second term. We integrate the second term, that is cos of 2 omega t with respect to omega t. We integrate it with respect to omega t. So the integration of the second term results in 0. Let us show that the integration of the second term results in 0. So this is the integration of the second term which results in 0. So the root mean square value of this alternating current is equal to under root Im square by 4 pi, the integration from 0 to 2 pi of d omega t. And we know that the integration of d omega t is omega t, and the limits are 0 and 2 pi. So if we simplify this particular equation, the root mean square value of the AC current will be equal to the maximum value by under root 2. If you know the peak value of the AC current, you guys can calculate the root mean square value of the AC current with the help of this particular equation. And this equation can be written as 0.707 multiplied by the maximum value of the current. So let us use these equations to do a few numerical examples. We do example number 3.2. Example number 3.2 says the maximum value of an AC current is 14.14 ampere. So this is the peak value of the AC current, and this AC current is shown in this diagram. You see, this is an AC current. This AC current varies sinusoidally with respect to time. Here is the maximum value of the current. So as the maximum value of the current is known, we can calculate the root mean square value of this current. The root mean square value of this current will be equal to the maximum value by under root 2. As the maximum value is 14.14, so we divide 14.14 by under root 2 and we get 10 ampere. So the RMS value of this AC current is 10 ampere. Now we are going to calculate the average value of the AC current, and keep it in your mind that for the calculation of the average value, we consider the positive half cycle of this AC current only. We will integrate this current from 0 to pi, and we will divide it by pi. We don't consider the full cycle of the AC current for the calculation of the average value. So in order to calculate the average value of this AC current, we use this particular equation. So in order to calculate the average value of the AC current, we use this particular equation. We have 1 over pi, the integration from 0 to pi of I d omega t. And we know that this is an AC current, and the AC current varies sinusoidally with respect to time. So we put the value of the AC current in the above equation. So we obtain this particular equation, which is 1 over pi, the integration from 0 to pi of the AC current. So we just put the value of the AC current in this particular equation. And we know that the integration of sine of omega t with respect to omega t is minus cos of omega t. So we integrate sine of omega t, and this integration results in minus cos of omega t. So the average value of the AC current is equal to the maximum value by pi. The integration of sine of omega t is minus cos of omega t, and the limits are 0 and pi. So if we simplify this equation, we get the average value of the AC current, which is equal to 2 Im by pi. And if we put the maximum value of the current in this equation, we get the average value of the AC current, which is 9 ampere. So keep it in your mind that you guys need to consider the positive half cycle for the calculation of the average value of the AC current as well as the AC voltage. Let us do another numerical example. So you see, in this particular numerical example, we consider a time varying current. If you look at the diagram, the current varies with respect to time, and the maximum value of the current is 2 ampere. And if you look at this pattern, you see this pattern repeat itself after 1 second. So if the pattern takes 1 second to repeat itself, then the time period of this waveform will be 1 second. So we can define the time period in these words as well: the time taken by a waveform to repeat itself, the time taken by a pattern to repeat itself is known as time period. So we know the time period as the time is along the horizontal axis. So in order to find out the maximum value of the time varying current in the following waveform is 2 ampere, we are going to calculate the root mean square value and the average value of this time varying current. We calculate the equation of this particular line, and we know that the slope of this line is 2. So the equation for this line is 2t. You see the time period of this waveform is 1 second, and the equation for this particular line, let me consider the line first. You see, we calculate the equation for this particular line. The slope of this line is 2. So the equation for this particular line is 2t, and you see the time is changing from 0 to 1. This equation is valid only in this time interval. So we calculate the average value of this time varying current. As the time is along the horizontal axis, we use this equation. The average value of this time varying current will be equal to 1 over t, where t is the time period of this pattern, the time period of this waveform, and then we have the integration from 0 to t of I dt. So we put the value of the current in this equation. If we put the value of the current in this equation, if we put the value of the current in this equation, you see the time period is 1. So we have 1 over 1, the integration from 0 to 1 of 2t dt. So we integrate this equation. The average value of this time varying current is equal to 2. The integration of t is t square by 2, and the limits are 0 and 1. So the average value of this time varying current is equal to 2 into 1 by 2. The average value of this time varying current turns out to be 1 ampere. And we calculate the root mean square value of this time varying current. As we have the time along the horizontal axis, this is why we use this particular equation. The root mean square value of this time varying current is equal to under root 1 over t. Then we have the integration from 0 to t of I square dt. So we put the value of the current over here. We know that the current is equal to 2t. We know that the current is equal to 2t. So we put the value of the current in this particular equation. The root mean square value of the time varying current will be equal to under root 4 by 1. 1 is the time period. Then we have the integration from 0 to 1 of t squared dt. And we know that the integration of t square is t cube by 3. So if we integrate the right hand side, the root mean square value of the time varying current will be equal to under root 4 into t cube by 3. The limits are 0 and 1. And if we simplify this equation, we get under root 4 by 3. So the root mean square value of the time varying current is 1.154. This was the second example. Let us consider another waveform. You see, this is a square waveform. The maximum value of the current is 2 ampere, and the time period of the waveform is 2 seconds. So let us consider this waveform. The time period of this waveform is 2 seconds, and you see, if we look at the equation, the current is 2 ampere from time t is equal to 0 to time t is equal to 1, and this current is minus 2 ampere from time t is equal to 1 to time t is equal to 2. Let me consider this waveform once again. You see, the current is 2 ampere from time t is equal to 0 to time t is equal to 1, and then this current is minus 2 ampere from time t is equal to 1 to time t is equal to 2. So we consider the complete cycle of this particular current. So we calculate the root mean square value of this current. As we have the time along the horizontal axis, so the root mean square value of this time varying current will be equal to under root 1 over t, the integration from 0 to t of I square dt, and there are two values of values of this current. We have plus 2 and we have minus 2. So the root mean square value of the time varying current will be equal to 4 by 2. Then we have the integration of dt from 0 to 1 plus the integration of dt from 1 to 2. If we simplify this equation, the root mean square value of this AC current, this time varying current, this is not an AC current by the way, this is a time varying current, will be equal to 2 into 2. So this is another numerical example, and the root mean square value of this time varying current is 2 ampere. So let us consider another numerical example. You see, this is another waveform. This is how the current changes with respect to time, but we have omega t along the horizontal axis. So you see, if we consider the equation for the current in this particular range, the equation for the current will be equal to Im into sine of omega t. So in this particular range, the waveform justifies this particular equation. So you see, we have the equation for the current. The maximum value of the current is 10, and then we have sine of omega t, but omega t is changing from 0 to pi. So this equation is valid only in this particular region. So let us calculate the average value of this current. So for the average value, we use this particular equation. We have 1 over pi, then we have the integration from 0 to pi of 10 sine of omega t d omega t. The integration of sine of omega t is minus cos of omega t, and if we simplify this integration, we get the average value of this time varying current. The maximum value of this current is 10, so we get 20 divided by pi. The average value of this time varying current is 20 by pi, and we get 6.366 ampere. Now let us calculate the root mean square value of this time varying current. We have under root 1 over pi, then we have the integration from 0 to pi of I square. This will be d omega t, I'm sorry, because we have omega t along the horizontal axis. So we will have I square into d omega t, and you see, I square will be equal to 100 into sine square omega t. So we put the value of I square in this particular equation. So we get the root mean square value of this time varying current, which will be equal to under root 100 divided by pi, the integration of sine square omega t d omega t, and we replace sine square omega t by 1 minus cos of 2 omega t divided by 2. So if we replace sine square omega t by 1 minus cos of 2 omega t by 2, we get the root mean square value of this time varying current. We get under root 100 divided by 2 pi, the integration from 0 to pi of 1 minus cos of 2 omega t d omega t, and there are two terms over here. So the root mean square value of the time varying current will be equal to 100 divided by 2 pi. This is the integration of the first term, and this is the integration of the second term, and the integration of the second term results in 0. So as the integration of the second term results in 0, so we get this particular equation. Root mean square value of this time varying current will be equal to under root 100 divided by 2 pi, and then we have the integration of d omega t from 0 to pi, and you know that the integration of d omega t is omega t. If it is omega t, so we simplify this equation. The root mean square value will be equal to 10 divided by under root 2, and the root mean square value is 7.07 ampere. Let us do the last numerical example. In the last numerical example, this is one complete cycle of the AC voltage, because the pattern repeats itself after 2 pi radians. So we need to consider the equation for the current from 0 to 2 pi. You see, if we consider the equation for the current from 0 to pi, so the current varies sinusoidally from omega t is equal to 0 to omega t is equal to pi, but the current is 0 from omega t is equal to pi to omega t is equal to 2 pi. So let us consider the average value of this the average value of this time varying current. So the average value of this time varying current will be equal to 1 over 2 pi. We consider the equation for the current from 0 to pi, and then we consider the equation for the current from pi to 2 pi, and you know that the equation for the current from pi to 2 pi is 0. So if we simplify this integration, the average value comes out to be 10 divided by 2 pi. The integration of sine of omega t is minus cos of omega t, and if we simplify the right hand side, the average value comes out to be 2 multiplied by the maximum value by 2 pi, and if we put the value of the maximum value of the current, we get 10 divided by pi. So the average value of this time varying current is 3.18, and we use this particular equation to calculate the root mean square value of the AC current. And by the way, we have d omega t over here, so this is d omega t. This dt should be replaced by d omega t. So if we put the values, there are two values. So you see, we have 100 into sine square omega t d omega t, and we have 0 square d omega t. Anyhow, we will use this particular equation to calculate the root mean square value of this time varying current. You see, this term is 0, and we replace sine square omega t by 1 minus cos of 2 omega t divided by 2. So anyhow, we get this particular equation, and then just look at this particular equation in the book. You guys will understand it from the book, and you see, we simplify. You see this particular equation, we get under root 25, so the root mean square value of this time varying current is 5 ampere. This is big enough for today. We will start the AC circuits in the upcoming